today we have two of our very young students here today. We're going to start with Jenna. Exactly what I wanted. Jenna Ehnot received her master's in science. Started it off wonderful. Jenna Ehnot received her bachelor's in science and ocean engineering from the University of Hampshire in 2022. Continuing at UNH, she is currently pursuing a master's degree in ocean engineering in marine robotics and autonomy. This summer, Jenna interned in the Autonomous Surface Vehicle (ASV) lab at the Center of Coastal and Ocean Mapping, where she intends to conduct her thesis research. She is currently looking into machine learning data sets for marine object detections and working part-time in UNH's Ocean Hydrodynamics lab. All you.
Hi. So, as Erin mentioned, I am part-time in the hydrodynamics lab, and this is a research project that I did with Tracy Mandel last year. It won't be my thesis, but it's still important, and we'd like to talk about it. So, I'll be presenting at the AGU on the seasonal variations in the biomechanical properties of American beachgrass in cold weather climates. So we'll start with the motivation. There needs to be a why behind every research project. So I'd like to think most of us are aware that coastal vegetation helps dissipate wave energy on our coasts. It's one of our best defenses against coastal erosion. It helps in sedimentation and sediment accretion, but there's little that we know about the hydrodynamic interaction with vegetation. We know that it's good to have plants on our coastline, but we're not yet able to quantify how much vegetation can slow down tidal events like overwash. So why do we study the real world? We want to be able to make more informed, realistic experiments in the lab environment and experiments such as flume flows with vegetation to then be able to make more accurate predictive modeling for the real world, like coastal flood models. So when we're looking at the equations of motion for flow through vegetation, we encounter this term Cauchy number. And the Cauchy number describes the drag imposed on the flow as a ratio to the bending stiffness of the vegetation. Shown here, I just learned how to use PowerPoint animations. So E, the elastic modulus is what we're interested in. The elastic modulus is a parameter that's intrinsic to a material and in essence is the stiffness of it. So it defines how does a material respond to loading? How does it deform in response to forces? But for plants, there's not really a lot of information on the material science of plants, and even less about the seasonal variation. So in places like where we live, how can we model things or coastal events with this vegetation if we don't know the parameters like the elastic modulus or how it changes over the course of a year? So our plant of interest in this study was Ammophila breviligulata, or American beachgrass. And it is native to the Atlantic coast as north as Nova Scotia and as far south as Georgia, and has become an invasive species on the West Coast, but that means our research is even more applicable. And it is a really integral part of our coastline. It's one of the most common grasses. It has a super dense, intricate root system that locks sediment into place, and its blades help pull sand out of the air when there's a gust blowing across the dune and helps with sediment accretion. And it's this really coarse perennial grass, meaning that like most plants in our area, it dies in the winter, grows back in the summer. So this is our plant of interest. And we were able to identify 3 locations on the New Hampshire coastline where we had observed sediment overwash or sediment recession from the shoreline with predominantly Ammophila breviligulata. These locations were Straws Point, and then 2 locations at Odiorn Point State Park. We'll refer to those as Odiorn North and Odiorn South. And at each location, we first established a grid over the entire area so that we could have some sort of spatial resolution within each location of where these plant samples came from. And from each grid cell, we would take 1 cluster of plants from each grid cell on a bi-monthly basis, giving us these plant samples that we would take back to the lab and then test. The intention was to do bi-monthly sampling on a year-long time frame, but due to some unforeseen circumstances and events that happened, we were only able to sample from August to December. So we still have a representation of summer to winter variation. All samples were tested within 10 hours of being pulled from the ground to reduce any sort of decay that they faced from being out of their environment. And since it was a kind of lengthy sampling process, we couldn't do all of the sites in one day, but they were all sampled within a week of each other. And in addition to studying the elastic modulus, We also took note of the total length and stem diameter of the plants. So once we had the plants in the lab, we performed 3-point bending tests on them. On the right is the Zwicky line machine. I wish it had a cooler name. But the Zwicky line tabletop machine allowed us to do a 3-point bending test with this upper loading die connected to a 100 Newton load cell, 2 support beams on the bottom, and we would rest our plant stem across it. So the upper load cell would move downwards at a rate of 10 millimeters a minute, and the machine would produce a time series of the upper displacement of the die, which is equivalent to the deformation of the stem, as a function of the force that the load cell experienced. So our area of interest from this time series is this linear region down here. The elastic modulus, or the elastic behavior of a material, is characterized by this linear relationship between the force that the material experiences and a linear deformation. So to quantify this linear deformation, we did a best fit of the line with an R-squared value of 0.99, and then we were able to identify the slope. And the slope represents the force over the deformation of the plant stem. And we're actually able to model the plant stem as a simple cantilever beam and do the statics equations that you would for the regular deformation of the beam, which we could rearrange and solve for the elastic modulus as a function of the slope of this line, the span length, and the second area moment of inertia, which we don't need to do any sort of solving for the second area moment of inertia. It's a property of the shape of our material, which for us is a cylinder. So taking the slope of this line, plugging it into the statics equation for a simple beam, we're able to identify the elastic modulus. So this was our preliminary data analysis. We just wanted to see what kind of variation do we have in our data. And the answer was, there's a lot of variation, unequal variation across the data set with, you can tell from the length of the box plots getting smaller and smaller as months go on. And also there's a presence of a couple significant outliers. So what we know about our data from the first round of analyses was that we have a non-normal distribution and unequal variances, which changes the tests that we could do later on. So our next step was to do a restricted maximum likelihood test, which helps us understand where the variation in our data comes from. And from this, we were able to identify that location has a relatively insignificant effect on our elastic modulus. We were able to consider this. We did this by fitting a linear model to our data with location being considered as a random effect. And it gave us a walled p-value of 0.5, which is relatively high, which means there's no significance. And the percent of the total variance that it contributed was 1.9. So out of all of the variation in our data set, location only contributed about 2% of the variation. So for the rest of all our analyses, we were able to consider elastic modulus as a function of month, not really include location. That 4 miles of New Hampshire coastline really didn't make a difference in all of our samples. So moving to our next tests, we did the Wilcoxon non-parametric pairwise comparison, which basically takes all of the possible pairs in your variables and compares them, as the name implies. And from this, we were able to tell between December and October, there wasn't a significant difference. 0.04 is relatively low for a p-value, but not as low as we'd like it to be. However, from August to October, there is a significant difference in the elastic modulus, and August to December as well, a significant difference. And this brings us to the quantification. So we know that there's significant difference in the elastic modulus between August and December and August and October. That's not necessarily surprising to us. We knew that plants die in the fall and winter, but we want to know by how much. So we needed to choose a parameter to identify or a parameter to summarize or characterize our data set by. And we ended up going with median because medians are relatively unbiased parameters of data sets, whereas means can be thrown off by outliers like we have here, here, and here. So looking at the median, you can see that it goes from about 1,600 in August all the way down to 700 in December, which is a factor of more than 2. So if we were to throw the elastic modulus of August into a hydrodynamic model for vegetation, but we were modeling an event happening in December, our Cauchy number would be off by a factor of 2. So what does this mean for us? There is a significant seasonal variation in E, excellent. Sometimes it's different by a factor of 2, depending on the time of the year. However, there's a need for repetition in this study. I will be the first to admit that it is a real bummer that we couldn't do a whole year of sampling. But even just from August to December, we were able to see a significant change. And that gives us the inspiration or the inclination to do more testing. An important part of the study was simply the development of a testing protocol. Like I said, there's not a lot of studies that have been done on the material science of plants, and having a protocol to follow is really important. So this is replicable by other places and universities. And we're interested in collaborating in order to expand this data set of elastic modulus for plants to include other species. So from this experiment, we're able to take this data and hopefully fall into this area between the real world and the lab environment to start filling in those gaps of understanding, so then we can better study our hydrodynamic vegetation interactions. So I'd like to open it up for questions.
You examined the difference between sites, but it looked like your sampling scheme that was a grid would also allow you to examine within site variability. Did you look at that, or is there any reason to believe, particularly with the complication of time, that there might be a change that all of the, I don't know, north ones or the ones farther from a beach or something thickens more or less or something like that within a site?
So that's an excellent point. Within a site, and a characteristic of these plants is that their size can depend on the salinity levels that they're exposed to. So plants closer to the beach are usually shorter and more stout. And then, but in our location, there was this tidal channel that ran through the back. So anytime there was flooding, these plants were also exposed to high levels of salinity. So while there is an influence of variation within each location, we didn't have time to really characterize how that changed site to site. We were more so interested in the bigger scheme of things between all of our locations combined. But that is an excellent point. There definitely can be a difference based off of the spatial variation at a location.
Okay, nice presentation. You mentioned 3 sites that were used. And do you consider whether all the sites had the same geology?
We didn't consider if all of the same sites or all of the sites had the same geology. That is an interesting point, though. They would be interacting with the water differently if they were higher up, but that's not something that we considered.
Does the beach grass, does it grow in a specific soil type, or is it kind of like quite adaptive?
So it likes sandy soils. I'm not sure about what other environments that it can grow in, but as far as I'm aware, it doesn't prefer salt marshes versus dunes. It usually just sticks close to the coast.
Gotcha. Thank you.
So for your current study, you were able to kind of say that the location didn't terribly impact it.
Mm-hmm.
But if you expanded your studies in the opposite direction of him and started looking at another state, do you think that would still be the case?
Yeah.
Yes.
So if we were to expand this to include other states, I think it would then become a multi-level experiment where you have to consider the location and the month. Multi-level experiments were above my statistical understanding. So once we were able to prove that location didn't have an impact, that was a relief to me. But if somebody else in the future wanted to do that, it would definitely be worth considering. It would just make it a little bit more complex.
How long did it take you to learn how to say the name?
Probably 2 weeks. It was one of those words that you would read it but not actually say it, and then you have to say it out loud. Oh, this is something that I've read a bunch of times, still don't know how to say.
Tamer, yeah, no, I said that right. Tamer earned his BSc in Naval Science from the Egyptian Naval College, served as a chief officer in the Coast Guard Brigade, then as a captain of a control gunboat in the Egyptian Navy. He started his hydrographic career by earning his Cat B in an IHO hydrographic course with honors from the Naval Oceanographic Office in the UK, then participated in numerous survey operations as a hydrographic surveyor in the Egyptian Hydrographic Department. In 2009, he completed his first master's degree in hydrographic surveying from the Egyptian Academy for Science and Technology, with the trophy for best thesis in seismic surveying. Thereafter, in 2010, he earned his second Master of Science from the University of Southern Mississippi while completing his long hydrographic course, his category A, with the U.S. Navy. In the Egyptian Hydrographic Department, his last post was the chief of the Egyptian Hydrographic Navy, the Egyptian Hydrographic Division, and was responsible for the production of the first Egyptian electronic navigation chart portfolio. In 2017, he retired as a captain from the Egyptian Navy, then worked as a freelancer geophysical surveyor for Fugro SAE. In 2018, he started his PhD in CCOM. His point of research is for a fully automated nautical cartographic solution. Tamer.
Hi, everyone. So, I'm Tamer. I'm sorry, my voice is not baby. So, I've been over here for almost 4 years right now, working with Brian Calder and Christus towards automating the compilation of electronic navigation charts through an automated nautical generalization model. So, today I'm going to be trying to present our research work so far, answering 3 main questions. So, the 3 main questions is why we need to automate, how we need to automate, and when to automate. And then I'm going to show you some results at the end. So according to the IHO, there is a bunch of scale bands on top of each other from the ENCs, starting from the overview, which is the highest level of detail. I don't know where they are. And then up to the harbor and berthing, which is the largest scale or the highest level of detail. So in any area, there are several bands on top of each other of the ENCs. And every time you zoom in or zoom out, you just switch from one band to the other. And in any hydrographic office, they have to produce all of those ENCs in order to cover the same area. And according to the IHO and NOAA, every band has an upper and a lower scale. So for instance, the overview, as you can see, 10 million to 1.5 million, and the berthing is 1,000 to 4,000. And in NOAA, it's slightly different, but the amount of effort that needed to produce all of these ENCs is enormous. So several steps are needed to be undertaken in order to produce an ENC in any office, starting from designing the production up to having an ENC database to maintain and produce ENCs. So in any hydrographic office, hydrographers and cartographers work together to produce any type of ENC, like a new ENC or a new edition, or even an update. And then after that, it has to go through a rank and then distributed network till it finally reach the end user. So that's a very long process, takes a lot of time. And in case of a critical update or green accident or anything like that, it has to go take the same loop again to reach the end user. So for sure, that's a very long process. It takes a lot of time and a lot of effort, and mariners are not happy with that. So luckily, I have to mention that over here in the US, these 2 steps we have to bypass it because thanks to NOAA, we have a website over here that you can download the ENCs free without any subscription. But trust me, everywhere, I think according to my understanding, everywhere else, you have to have a subscription and pay for that. And that's a lot of money. So that's the question why we need to automate in order to minimize the time and effort and cost for producing ENCs. Another reason would be the amount of overlapping between the same scale band. So in the example over here in Puerto Rico, you see every color represent scale band. So you see the amount of overlapping between ENCs. And where is this coming from? It's coming from the paper chart. So most hydrographic offices, when they started producing ENCs in the mid-90s, they did that by digitizing the paper charts. And in paper charts, you have to have a significant overlapping that's required because the mariner needs to switch from one map to the other in order to navigate. So that's a good thing in the paper chart. But in ENCs, that is not a good thing. I'm going to show you the consequence of that. Another example over here, East Coast, you see the amount of overlapping, and this, we call it the puzzle layout. So real life in EGDIS, and EGDIS is the electronic chart display information system on board any vessel. And according to the IMO, which is the International Maritime Organization, it's mandatory to have an EGDIS system on board any vessel. And the ENC is the main base of the EGDIS. So the EGDIS integrate all other sensors on board the vessel, like the GPS, the ARBA, the AIS, radar. So the mariner would be able to see the situation and take the right decision from the EGDIS. But this overlap would lead to something like that. You can see over here, discontinuity between depth contours and depth areas. These are two cells over here. You know where is the laser? Everyone?
Yeah.
Yep, okay. Good. So over here, this is one cell and this is the other cell. So you see over here the discontinuity of the depth area and depth contour. And for sure, this might cause lots of problems. For instance, it might trigger false alarms, which might lead to something called the mariner's deafness. Because the mariner might disregard important alarms because of a number of irrelevant ones. So that's an example. Another example, as you can see over here, generalized contour and under-generalized contour. And this for sure give confusion to the mariner. Another example over here, discontinuity between two depth areas and depth contours. And this for sure something that needs to be avoided as well. So the time that can be saved from automating the production would be steered in hydrographic office to solve problems like that. And another problem would be the metrification over here of the ENCs in the US, because everything in the US over here was compiled in fathoms and feet. And when it's displayed on EGDIS, it's displayed in meter. So you see this contour interval when it's displayed in EGDIS. This gives some confusion to the mariners as well. So again, by automating the production, we might save some time, and hydrographic office of NOAA over here can steer the effort to solve problems like that. So that's the question why. So in 2019, NOAA started to plan to rescheme the coverage from this current puzzle layout, as you can see on the East Coast and the West Coast, I hope you can see it, to a perfectly gridded system like that. So in this system, each 16 cells of band 5, for instance, can fit perfectly on the next scale, which is band 4, without any overlap whatsoever. And this will solve all the problems. But for sure, in order to do that, you have to start with the highest level of detail, which in this example over here in New York Sound area, this is band 5, which is 1 to 10K or 1 to 20K, band 5. When they're done with band 5, you can go to band 4, and then from band 4, band 3, and so on. So starting from the highest level of detail, you need to finish, first of all, the highest level, which is band 6 or band 5, according to the importance of the irrigation area. So in order to go from A over here, which is the current puzzle layout, which is almost everywhere, not everywhere, some countries are using the gridded system right now, but most of the world, this is the case. So the perfectly gridded system, you need a plan for time. And in NOAA, by 2019, they started planning, and in order to finish only one band, which is band 4, starting in 2020, it would end in 2024, just 5 years to finish only one scale band. Then from there, we can go to band 3 and then band 2. And how do we do that? By generalization, which is the main research, my research, generalizing the features. So on the example over here, this is the Isle of Shoals over here in Portsmouth, quite sure everyone is familiar with that. So you see a bunch of land areas, islands, polygons like depth areas, contours, sounding, lots of features. So in real life, the cartographers do the generalization, and the generalization operators like aggregation, combining, selection, collapsing, simplifying, smoothing, manually, or maybe semi-manually, in order to go to the next scale, which is band 3. So what happened over here is that the cartographer decide which is the dominant feature that has to maintain on the next scale, eliminate the rest, or maybe merge a couple of islands, merge a couple of depth areas, select some soundings, select some aids to navigation, which is important. So this is done mostly manually. And then from there, from band 3, the same to band 2, then band 1, so on. So my main research question was, can we automate this process? how far can we automate this process and how safely can we do it? Because safety is very important in navigation for sure. The answer to this was, yes, we can do that, but there are some challenges with it. So has this been done before? Has been done in the topographic domains. Some offices has been already done it in generalizing topographic maps for land maps, but in the nautical domain, it hasn't been done yet. And why is that? Because of the constraint, the nautical constraint. There are 4 types of constraints that had to be respected all the time during generalization: safety, topology, eligibility, and morphology. So to give you an example on the safety constraint, if we have a pit and a peak like that, 3-meter peak and 12-meter pit. So during generalization, we can eliminate the pit, remove the contour and the sounding, but we cannot touch the peak whatsoever for safety. Another example would be while generalizing a depth contour, and this is 2D contour where you have a shallow side over here and a deep side over here. So during generalization, if we use any kind of software or algorithm that does not respect safety, this would be the output of it, which is unsafe generalization. And why is it unsafe? Because there's some areas over here, as you can see, those areas has moved from the deep side to the shallow side. And vice versa, from the shallow side to the deep side, which is clear safe violation safety. So the accepted generalization would be this green line, which is totally biased toward the deep side. So the model or the algorithm that will do the generalization had to respect this safety constraint. That's why it's a bit challenging to do this. Second constraint, which is very important as well, first 2 for the hard constraint that cannot be violated for a chart to be valid. Topology constraint, it means that there should be no gaps, no overlap, no self-cross of any feature in the map. So for example, if we have a land area like that, you have a coastline and close by, can we get rid of this? So if we have an island close by to a land area like that, when we start generalizing, if this distance, according to the scale, is smaller than a specific tolerance, then we have to merge this island to the land area. And when we do that, we have to do that without any gaps or overlaps. And that's a very important constraint as well that had to be respected during the generalization. So these first 2 are the main important constraint that we have to respect it during generalizing, and that's what I'm focusing on my research. The second 2, which is eligibility and morphology, can be violated. It's more flexible. So in order to do that, the second question is when. It's not. It's okay. So in the ENC world, there are more than 170 features. And when I say a feature, the land area is a feature, capacity is a feature, sounding is a feature, beacon is a feature. So we have about 170 features according to the S57 or the new S101. So in order, for the sake of the proof of concept or for the research, I've selected a group of them just to prove the concept. And those features belong to 3 main primitive: polygons, lines, and points. All those features. It's either polygon or line or point. So the most important polygons are the group 1 polygon, which is called the skin of the earth. And anyone who's using ENC would know what's the skin of the earth. Those 7 polygons that are the base of any ENC. And there should be no gaps or overlap between those polygons. So these are the most important, and it has the higher hierarchy level in the model. So starting with the polygons, and then comes the lines, second hierarchy level. The polygons control the lines. So when the land area is generalized, coastline, which is edging the land area, will be following the generalization. And then the last one would be the points, which are used to as barriers, just like soundings or aids to navigation or wrecks, obstructions, any point object of the ENC. So this is a very important step in the model to define the hierarchy level of all the features, which is the most important feature to be maintained. So when you start to generalize, there are 100, let's say there are 100 features on the map, and you have to save 20 features. So which one will stay and which one will be eliminated according to this hierarchy level. To give you an example, over here, this is land area, which is in the middle over here. And silicons are the artificial coastline, like a jetty, like a pier. And this is the natural coastline and soundings and its navigation. So each feature, those features has to be assigned one geometric relationship and one generalization relationship. For instance, the land area is the skin of the earth, geometric and shared feature. Then the coastline is edging the land area and sharing its geometry. Then the silicons is edging the land area, but will be used as barrier. So each feature of all the selected feature will be assigned one geometric relation and one generalization relation, and this will be defined in something called the GRS, which is Generalization Rules Spreadsheet, where all the tolerances and all the rules and all the relationships are defined on this GRS, and this is what controls the model. Another example over here to understand this, if we have a land area, the land area is a skin of earth and sharing the edge, which is the coastline. We have the coastline, which is edge and shared. The silicons is edge and barrier, and the aids elevation are interior and barrier. So when we start generalization, the coastline, the natural coastline will be generalized, but this construction will maintain its geometry, and this L-shaped jetty will be deleted. Just like that, when we do the generalization, so the coastline will be generalized, the artificial coastline will be maintained, and the L-shaped jetty will be eliminated. Just an example. And this is all controlled by the GRS. So that's answering the question when to generalize each feature of the ENC. So this is the model in ArcGIS Pro, in the Esri environment. And starting from the source data, which is user input, I'm going to show you three elements are used as user input. The source data, which is normally the highest level of detail ENCs, let's say band 5. And then the area of interest, which is the border of the new ENC that need to be generalized, and the GRS, which is the generalization rules spreadsheet, where all the rules and the tolerances are defined. So once the model starts running, create 3 different geodatabases, temporary databases. The first one is called generalization database, which is a copy of the main database, but simplified. So all the subdomain, all the tables, everything is simplified, but a copy of the source data, and everything is backed up in the generalization database. The theme database is the database where all the processing takes place. The scratch database is where all the eliminated features goes to. And then the model runs in 5 phases: prepare, phase 1, phase 2, phase 3, finalization. Takes about 10 minutes to run. And the output would be the same area of interest, but generalized data with no topological errors. So that's how we are running the model in Esri. That's a flow chart of the model. And this over here is just the 5 phases in ArcGIS. It's about 30 submodels. They all run in sequence in 10 minutes. So to give you an example of one of the submodels, this is the simplify shared submodel from the generalization database. All the features over there. The features are extracted to the theme database from the GRS. We take the tolerances, the relationship of the features, and then the model will iterate through these features to simplify all the shared polygons and shared lines, assuming all other features will be assigned as barriers. So all the soundings, the position of the sounding will be respected, the position of its navigation will be respected during the generalization of the features. And this is the model in this submodel in Model Builder, where it can be modified. And I'm using the band simplify algorithm by Wang and Muller in order to do the simplification of the polygons and the lines. And this was the best algorithm compared with other algorithms available with ArcGIS. And for sure, every submodel can be modified in Python. So over here, this is just capture of some of the main important submodels, starting from the input database. The model runs in sequence. Some of them are pretty straightforward and some of them are a bit complicated. And then the final output would be the same database, but simplified or generalized. I'm going to show you some results right now. So in order to implement the model, you have to select an area, implement the model with different scenarios. So according to NOAA, this is from the NOAA website, colors over here represent all the green cells are completed cells, which is available to the public. You can download it free again. And the red cells are still in work by the Marine Chart Division, the MCD. And the gray one are still planned. So 3 areas were selected in order to implement the model with different scenarios. Area number 1 was having perfect edge matching. I say edge matching, that all the features meet at the borders of the cells without any inconsistency. Number 2, this area has some edge matching. And number 3, case where you have mixed data from band 5 and band 4. So these are the 3 main scenarios that might happen in real life. And over here, this is the current status of NOAA ENCs. As you can see over here, this is band 5. About 13.8% is available to the public, and still 85% are planned. Same for band 4, and nothing has been done in band 3 and band 2, and band 1 for sure. So there's a lot of work that needs to be done, and a lot of time will be taken. So hopefully this would help. So that's the first area, New York Sound area. It's called Block Island Road. As you can see over here, these are 16 small cells, 16 band 5 cells, scale 1 to 20K. And this has perfect edge matching. There good edge matching between those cells. All the lines, the contours, the depth areas meet at the borders. Over here, there's no inconsistency. So the model runs in about 10 minutes, and the output has 0 topological error, and this is 1 to 80K. And these for sure are only the selected features, which is about 13 features from the overall. This is just the pre-generalization, post-generalization number of features from 20K to 80K. So it's about 21.4% of the data has been maintained in the 1 to 80K, again, with 0 topological errors. Another example over here, Long Island Sound area. But over here, we have a couple of cells where we have inconsistency edge matching. As you can see over here, this contour is not over there. The contour does not meet over here. The same for this cell. So when this is the input for the model would not generalize those couple of cells. Still generalize the rest of all the other cells with 0 topological error, but the output would be something like that. With the 2 cells, just generalize those features and kept it like that. It doesn't merge them, it doesn't join them, or simply just simplify them. So if this is the input, this would be the output. The third example is when we have 7 cells from band 5, and the rest of it is band 4. So we just clip the data over here and merge them together from the input database, and the output still is band 4, 1 to 80K, with no topological errors. So back to this. So as I said, the model output is 0 topological error, but the most important one is safety. But until now, the available tools in ArcGIS does not respect the safety constraint, fully respect the safety constraint. So we had to develop a model, a submodel that can detect the safety violations in the output. I was asked to do that. I did it. And this is the model, the submodel. It's called safety validation tool. We just compare the pre-generalization database to the post-generalization database. in three main stages. And the output of this would be all the safety violations in the output. This is the model, the submodel in Model Builder. These are the three stages, and for sure, again, it can be modified in Python. The last one, just to give you example or the result of the safety validation tool. So this is the pre-generalization database or the input. As you can see over here, the contour in that areas, and over here is the generalized or the output of the model. So the first step of the safety validation tool detect all the difference between the two databases. So the green over here represent all the polygons, all the areas where safe. So the contour has moved from the deep side to the shallow side. Whereas the magenta color represent the safety violation. So the last step in the model or in the submodel, the tool is to detect only the safety violation and sort them in a geo table like that with the area and the perimeter for the user to modify it. Some of them will be very small to scale, can be neglected, and some of them might need modification, manual modification. So yeah, that's the product or the end product of the safety validation tool. For sure, there are lots of things that need to be enhanced in the model, lots of things that can be for future work, but right now, this is the output, and I believe it can be implemented for all the features of the ENCs instead of only the portion, as long as they all belong to the three geometric primitives, which is polygons, lines, and points. Thank you. Ready for any questions?
Very nice presentation. I'm wondering, does the generalization, does it allow sort of jumping around, or do you have to go sequentially through levels? So
Jumping around. What do you mean by jumping around?
Could you go from the
Yeah, I have to start. Okay, if I understand the question, I have to start from the highest level of detail, which is the largest scale data, to the smaller scale.
right? But could you go to the small from the highest detail all the way to the lowest, or you have to go all the way down the chain sequentially?
Okay, I got your question. So that's, we call it the star approach or the ladder approach. So from the database, which is the highest level of detail, we can just generalize the second level, which is band 4, from band 5, go to band 4. Then from band 4, we go to band 3. Then from band 3, go to band 2. This is called the ladder generalization. And the star generalization is going from band 5 to band 4, and from band 5 to band 3, and from band 5 to band 2. So the model which I'm using over here, we are implementing the star approach from the highest level of detail, which is band 5. I'm generalizing to 1 to 40K, which is the lower limit of band 4, and then 1 to 80K, which is the highest level of band 4. And then from there, again, from band 5, we can go to band 3, but it hasn't been implemented yet in the model.
Okay, I was just curious to see if there was sensitivity between those two. If you do the same generalization in the different ways, do you see semantic differences?
That's a great question for every cartographer. Always compare between the star approach and the ladder approach. Each one of them has advantage and disadvantage. So the advantage for the star approach or for the ladder approach, that all the features that are generalized from band 5 to band 4 will be maintained from 4 to 3 and 4 to 3. But if you have any error, it will be accumulated. Whereas from the star approach, it's completely different. That's what I'm using from the highest level of detail, band 5 to 4, and then from 5 to 3, and so on. But again, what I did over here, the implementation is only from 5 to 4, the two levels of band 4, which is 40K and 80K. As I showed you in NOAA, right now they're working with only band 5, and when they're done with band 5, they're going to, in some areas they're working with band 4, but mainly they are focusing with band 5, the highest level of detail. In some areas there are band 6, which is the harbor band, the highest level of detail, very, very high resolution data, but it's very rare. I hope you answered the question.
Yeah.
I have two questions. Earlier on in the talk, you mentioned there was a tolerance for generalization. So if there was an island, certain a certain distance, you would have to generalize it within the landmass. Does that change? I'm assuming that changes with the different bands.
Sure.
Okay, so it
this,
does-
this distance is millimeter to scale. So this millimeter to 1 to 10 is,
millimeters of chart scale.
so we say millimeter to scale, 1 to 10 is different than 1 to 50, and it's different than 1 to 80. It's just a millimeter to scale. But that's a good question, because he didn't say that for the model, it should be a GRS or a generalization rules spreadsheet for each scale because of this, because of the tolerances and the rules that are applied for each scale. Future work again would be to have only one GRS for all the scales that can be implemented for all the scales. So there are lots of things that can be done. Question, thank you. Another one.
Another one. It also has to do with scale, but in relation to the safety violation pool. Can you set like not limits, but like a buffer on the safety violation pool for the different bands? Because something that is a safety violation in one band, in the highest resolution band, isn't necessarily going to be a safety violation in the lowest resolution band because of.
That's a point of discussion between us all the time. We are arguing, or we are trying to prove that in this case, since we have the highest level of detail all the time, because in the past you have to respect safety in all scales because you don't have the other scales available. But in this case right now, when you zoom in or zoom out, you will see the highest level of detail beneath it. So even there is a small safety violation, we can live with it, because if you zoom in, you will see the whole data, the largest data. So there is a tolerance for that we can accept some safety violation for the smaller scales, assuming that we have the largest scale. So when we zoom in, we will see all the data.
Thank you.
So you're saying you're using the star approach, and hypothetically, if you had an error going from band 5 to band 4, would that error, and then in the star approach, you redo the thing from band 5 to band 3.
Yep.
Would you not still trip and get the same error, or is what's going on underneath the hood?
Assuming that band 5 is the highest level of detail and the best data available, there should be no errors in this database. And then the model would be implemented on this database to create the band 4 and then band 3. So there will be no errors accumulated in this star approach. The error accumulate in the ladder approach, because when you generalize from band 5 to band 4, if you have a slightly error on band 4, so when you start generalizing band 4 to 3, you will have the same error, but it might be exaggerated in band 3, and then from band 2, the same error will be exaggerated.
So is there you're doing the manual inspection, the safety violations for depth safety issues.
Yep.
If there's any dangers to navigation that are being removed between the scales, is there any sort of manual inspection of those features to make sure you're not moving anything erroneously?
Yeah, that's a good question. So the dangers to navigation are points, and the points are dealt differently. So the points are all selected. We select the soundings, we select the aids to navigation, we select the dangers to navigation. So each one of them has a separate criteria, or separate algorithm we select. And the best thing in the model that can implement any kind of algorithm, it's flexible, because the generalization rules spreadsheet has a tab that all the tools are sorted in it in sequence. So if you want to remove the sounding selection algorithm and add a new one, if a new research reach something that respects safety, which is the case in our case right now, we have a sounding selection algorithm that respects safety, and there is another one that respects the safety for the contour. We can modify that, but this has not been done yet. But answering your question, the points are used as barriers, so their positions to be respected all the time. It's about how you select these features. So if you write the code that you need to maintain all the recs, don't touch any rec, or if there's a couple of recs that are about this distance at this scale, you can just remove one of them and leave the other. So when you zoom in, you'll see the other two, but when you zoom out, you just see one of them. That's according to the code that you're gonna write.